Hello, everybody. Can you hear me?
Yes, Professor. Good afternoon.
Good afternoon. How are you today?
Yeah, I'm fine. How are you, Professor?
Yeah, very good. Thank you. So, thank you for coming for last module, design of a seawater desalination plant. So we will today, we will discuss about how we can design a seawater desalination plant. So what's the seawater characteristics, and then what's the current desalination status and numbers. Also, we can think about a little bit of chemistry, not much in-depth chemistry, just general chemistry knowledge and some information we can cover to better design our seawater desalination plant. Also, we can discuss how we can make a membrane. What's the mechanism to remove the seawater salt and water? The water molecule is very small, like 0.6 nanometer size, and then salt, like sodium chloride, magnesium, potassium, and calcium, so many salt dissolved in seawater. So they have also very small molecule. So how we can separate water molecules and other salts. So we need a little bit of mechanism so that we will discuss about the membrane, how this semi-permeable membrane can separate your water molecule and salt. And then finally, we can put together this reverse osmosis membrane as a module. So we can make a larger scale and commercial scale. So in this case, how to design this module numbers, module configuration. So there are a lot of design parameters. And that's what we have to understand today. And finally, computer-aided software. So we have Wave software to better design your seawater desalination plant. So that's the we will cover today. So how many people? Oh, yeah, okay. Today, yeah, how many people have you looked at your recorded video and the materials and some of the reading documents? Have you ever looked at all the detail? Because today I will not cover every slide. I will just extract the most important slide to make a better understanding of the design of seawater desalination plant. So if you need any detailed information, so you can go back to your slide and there you can see more detail. And okay, so we can have just a brief discussion for feedback. So already you have experienced stakeholder engagement for your first module. And second module is about the wastewater plant design. And this module is the seawater desalination plant design. So far, yeah, what's your experience and then how you can see from your design and then some socio-technical issue from this subject. So if you have your experience, it's too difficult or too general, or it's very much time consuming. So if you have any comments based on your last two modules, yeah, possibly including your this three module. So if you can share a little bit of your feedback, do you want to have any feedback from this subject so far? Amit.
Yes, professor. Yeah, basically, yeah, I'm enjoying working on these modules because it's basically related to my my, professional sector. So basically, yeah, and there's no actually again feedback. I'm enjoying it.
Okay. So what's your most favorite part of this subject?
Yep. Up to now, yes. Basically, if I go by the assessment parts, so basically the stakeholder management was interesting thing for me because I get to analyze all the stakeholders parts and how they can engage, how they can play a role for the bringing up the project. And after that, for designing of the MBR and making comparison with the activators class process that is prevailing treatment plan at Malabar. So basically, this is the most interesting part for me, and I get to learn how to develop the existing treatment facilities with a new innovative ideas that can actually come to mind or we can find out.
That's great. Oh, that's the interesting, your favorite point. How about Amal? How about your experience so far for this 42991? And then what's your favorite part of this subject?
My experience so far is pretty good. Like I'm having fun with this course. I have learned a lot, like with the stakeholder engagement and designing a MBR treatment plan or wastewater treatment plan. And like I'm learning a lot, especially with the designing part.
That's great. So can you be a water treatment design consultant based on this subject knowledge?
Not yet, but like I'll try, you know, like
All right.
with
Okay.
more with more studying and experience with this particular part.
Okay. How about Ella or Illa?
Hi, it's Ella.
Okay, sorry, Ella, please.
No, that's okay. No, so I really enjoyed the layout of this subject where it was like 3 blocks.
Yep.
And I really liked the first assessment where we got to look at different countries and what they were also doing.
How about the wastewater treatment plant design and seawater desalination plant design? Are you also interested in this kind of design for the plant?
I like the on-site stuff more than the design, but it's
Okay.
nice to know and seeing like how it happens.
I see. Yeah, we wish we could visit one of the water treatment plant, but because of this pandemic, yeah, everything was a little bit limited. But yeah, we will see whether we have opportunity next semester or next year. So I will let you know if you are interested in joining some technical tour or excursions. So please yeah, join us later on. How about
Thank you.
Jiaming Teng?
Hello, Professor.
Yep.
Yep. Actually, I really enjoy this subject so far because I learned a lot of knowledge about such as the engagement plan and the design process of the water treatment and wastewater treatment. Actually, I learned something about the treatment in my bachelor, and actually, this subject helped me to deepen my understanding of this process.
So what's the most difficult part from this subject for you?
up to now, I think it's MBR design part.
Okay. So MBR design. So it's difficult for the understanding the biological process or understanding membrane process. Which part is the more difficult for you?
I think I'm more interested in the membrane part.
Membrane part.
Yes.
All right. So CO2 desalination plant today module is very much a membrane related design. So I'm sure that you'll be much more familiar than membrane bioreactor.
Yeah, that's good. Thank you.
Okay, thank you. Jono.
Hi there. I'm on public transport, so it might be a bit loud, but I've really enjoyed understanding like the water waste management around Sydney. And then probably one thing I found difficult is understanding the chemistry behind like the sludge and the biological processes.
All right, yeah, it's true. Yeah, if you are civil engineering or mechanical engineering or physical related knowledge and skill, so definitely chemistry is more difficult to understand. What's the pH and what's the suspended solid, total dissolved solid, the sludgy related, all the BOD, COD. So it's true, but that's the minimum. Yeah, minimum. Just a water indicator. In fact, it's not really in-depth chemistry. So if you are working on the water area, I'm sure that you'll be very much familiar with all this terminology. Okay, so we have a last person, Muyao Bo. So how about your experience so far? Muyao? We can't hear you.
Can you hear me?
Yes, we can hear you.
Okay. Actually, when I I was lit. I had well. How to say? I'm not so much on know about the treatment about the seawater because when I was undergraduate, my major is focus on the water in the city, and I think the seawater treatment is very interesting.
Okay, thank you, Muyao. Okay, so today, yeah, we can start our main task of seawater desalination plant design. So how many people look at our canvas? So let me share our canvas and then just explain briefly. Can you see the canvas? Is it okay? Everybody can see my canvas?
Yes, Professor.
Okay. So if you look at the your 42991 canvas, so you can go to the block 3. So you can see the what's the overview. Just in case if you have not looked at this canvas, I really recommend you to look at this one first because there are a lot of information you can study by yourself rather than the only this extracted and important live lectures. So what's the objective of this module? So advanced water treatment technology and design was a guide to selection of the water treatment process, membrane technologies, and one of the most important part is the computer-aided membrane process design using water application value design. Today, we organized this computer-aided design software. So if you cannot install this software, or if you cannot use this software, so you can go to the building 11, basement 1, room number 230-240. So all the computer already installed this Wave software. So some of them, they have a problem because of the Macintosh. So some of them, the computer installation requirement is not really well fitted. So every year I have faced a little bit of issue for this kind of software installation. So if you have not installed, or if you just want to use a university computer, so you can go to the room 230-240. So you can access the Wave software on the computer. Then you can do your assignment as well as so today we have booked our computer room from 6 to 9 p.m. Yeah, that's the reason why I have organized these lectures from 4 to 9. So you can go to the computer room and then you can join. So anybody has a problem to install the Wave program, Wave software in your computer? Looks like everybody perfectly installed, right? So nobody has any answers. So that's great. So you can install and then you just try to play a little bit, and then I will also give you some of the tips today. And if you go to the next, this is the basic reading material and videos. So what's the books? Efficient Desalination by Reverse Osmosis. So reverse osmosis is the most important technology to design your seawater desalination. So you can look at this book if you want to know more detail. Also, Desalination of Seawater. So this is the ebook. So most of them are ebooks, so you don't have to purchase the hard copy. So just download your PDF file, and then you can go more in-depth, detailed information for your seawater desalination. Also, you can look at the guide to selection to water treatment process. So which kind of technology would be the best for your water quality, and then water treatment design. Also, water treatment plant design challenge. So what kind of challenge we have? Also, you can see the several videos to see what desalination plant in Sydney. And we have reverse osmosis mechanism, how they separate water and then salt molecules. So you can look at some detailed mechanism video animation. Also, this is how they are fabricating the outer membrane module. And this is the pressure exchange in post desalination plant. And this is the pressure exchange device. And this is the energy efficient desalination. So when you have a desalination plant, so desalination plants recognized as a energy intensive technology. So how we can design energy efficient desalination. So you can see from this slide, and you will learn a lot from your reading materials and video. So that's the basic requirement you have to look at carefully to do your assignment 3. And you need also software Wave, which is the water application value engine. So this is the useful for your designing for seawater desalination or wastewater reuse, so ultrafiltration, reverse osmosis, ion exchange process into one comprehensive tool. So so using a common interface. So it simplifies the design process and ultimately helps to reduce the time needed to manage your water treatment system. So mostly people utilize the basic Excel file or basic your manual calculation, but it takes time. Also, you may have a lot of mistakes. That's the reason why this software, you can easily reduce your errors, as well as you can make a very quick your design of your membrane process and seawater desalination, wastewater reuse. And this will also give you what's the user manual in this link. And this is the installation procedure. So you can go to the website and log in, system requirement, and you need to download. And you can have unzip the folders, right click on setup, and you can also have a lot of detailed information here. But mostly, I'm sure that your computer is already installed this kind of operating system, so you don't have to worry about too much manual installation. I'm sure that most of people, if you download and install and click the setup, so you can easily install your software in your computer. So that's the installation and then training lecture video. So you can see from this video how you can download and how you can install your software, and then how you can utilize. So you can watch this video and then you'll be more clear. So how many people already look at this video? I hope everybody already successfully installed this software and then try a little bit. And if you go next, so block 3 lecture slide, so you can have a lecture slide assessment 3, design of advanced seawater desalination plan. So let's click here. So it goes to your assignment 3. Already you have a very familiar with assignment scenario. And this is the assessment report format. And this is the assignment task 3. So you can see what's the format, cover page, originality statement, and then table of content. So what's the abstract executive summary? And background of your scenario, why we need desalination plan, what's the importance related issue of the desalination for future water security in Australia. Also, based on this lecture, so you can independently design the desalination plan. So this is the assessment questions. The process flow chart clearly shows your selected intake design, the pretreatment process, reverse osmosis process, and any other relevant processes. A detailed design of the RO process, clearly describing key parameters such as types of membrane, number of banks, stages, vessels, element, and recovery. So this is a little bit specific terminology. So we will cover what's the stages, what's the pressure vessels, what's the element, what recovery we are talking about. So we will discuss during this class. So you can use Wave software. So you need to install the software and then utilize the software for your assignment. You should also clearly discuss what you have done to optimize the auto process design. How do you ensure that you have satisfied the boron limit of 0.3 milligram per liter? Also provide a comprehensive review on the impact of the brine. So after you remove the also salt, so we have a very high concentration of the brine. So what's the impact of the brine disposal on cuttlefish? Also propose relevant option to mitigate any adverse effects of brine disposal on cuttlefish, taking into account both economic and environmental consideration. Also, you need to look at the shutdown and restart plan. So we have a lot of raining for last couple of years, especially this year. So our Waragamba Dam, also all the dams, plenty of water. So in this case, we don't have to operate desalination plant because desalination plant is energy intensive. So we don't have to just remove the salt because we have a lot of fresh water in dam. So that in this case, we have a shutdown and restart planning of a desalination plant. So how we can shut down when you have a 60% of dam level or 50%, 40%, depending on the dam level. So we can try to make a scenario how to shut down, how to restart. So depending on your dam level, how we can make this kind of planning. So you can also mention about this kind of point. And conclusion and references, already you know how to utilize the reference software. And what's the others for assessment? So marking, then some of your English and the structure and sentence and grammar. So they are all important to make a professional report. So that's the we have to do by 30th of May. So that's your last task 3. So do you have any question for your task 3? What you have to do for your assignment 3? So everybody very clear. So that's great. So we can follow this outline, and then you can complete your last assignment 3. And you can see the lecture note A, B, C, D. So that's all the detail. You can see in your PDF file. However, today I just extract a very important slide rather than covering all the detail of the slide. So you need to look at this slide carefully if you want to know more detail. And we have also video how you manage the all the design related issues, so how to utilize the software, energy efficient desalination. You can look at all the detailed lecture note. And this is tutorial question. So after PDF file, I just selected some simple tutorial question, which is useful to design your assignment 3. So if you understand this simple tutorial question, also we have answer here. So you will get the better idea how we design a seawater desalination plan. And this is the software of the wave. So you can download from your website. Also, you can download from here, even though version would be a little bit different, but I don't think that's the issue. Just version 1 or 2 difference, it doesn't really make any difference to use this wave software. to complete your assignment 3. You can download the Wave software, and then example of the assignment 3 was available. This will be given to after this class. So if you go to the module, so today up to here, tutorial question, but after this class, yeah, I will upload your live video and lectures, as well as I will share some software program and then example of the assignment 3. So you can look at carefully all the what you have to do for your assignment. And then 20th of May, 2 weeks later, we will have a consultation meeting. So if you have a time 4 o'clock, 20th of May, so we will discuss about your assignment 3. So hopefully you can start your assignment 3 before that, and then bring your question into the consultation timing officially. And then you have another 10 days to complete your assignment 3. In the meantime, so we can organize individual consultation meeting. So if you have any question, if you have any kind of discussion, you can send the email, or we can organize a meeting. Also, we can have a face-to-face meeting. So my office is the building 11. So you can come and visit us before you visit, and then just make a little bit of booking. So just make sure I'm available in the office. So that's the we have to do. So that's the all about the Canvas. So that's the what we can complete the block 3, assignment 3. So do you have any question on this block 3 so far in the Canvas information? Looks like everybody very clear about this Canvas. So let's go for our slide. Can you see slide?
No, we can't see them.
No, you can't, right?
Can't.
Let me share again. Can you see slide?
Yeah, all good now.
Okay, that's great. Because I'm utilizing the 2 monitors, so let's make a little bit confused which one is the correct one. Oops. Can you see my mouse?
We can see it.
Okay, that's good. So I can use this. So these are content for today. What do we have to study to design a seawater desalination plant? What key terms used to describe the membrane processes, water quality parameters for membrane processes, introduction to reverse osmosis, design of reverse osmosis, case studies, seawater desalination plant, and water application value engine, integration of water treatment processes. So let's look at the general information of desalination in the world. The global seawater desalination capacity. So we have 6 major desalination plants in the major city in Australia. But if you look at the overseas, as you expected, the Middle East country, they have a lot of seawater reverse osmosis RO desalination plant. So Saudi Arabia, UAE, and followed by also United States, Netherlands, UK, Italy, Spain, also South Africa, Chile, and Asian country, Japan, South Korea, also India, and China, Hong Kong, Singapore. So if you look at the last 10 years, we have BWRO, the British water reverse osmosis, SWRO, seawater reverse osmosis, and this is the summer desalination. It's like evaporation using your heat. So as you can be seen, so summer desalination is very much stable, and then seawater reverse osmosis exponentially growing. Also, BWRO, they have a little bit of growing for the desalination. So overall, we have more desalination required in the future because so most of people, they like to live near the coastal line, and then so more people get together, and then you don't have enough water resources. The last dam is very much limited, and then your groundwater cannot utilize. Also, river water is also we have to protect so that the reliable water source is seawater. So seawater desalination is becoming more and more important. That's the reason why Sydney we have a desalination plant, and Melbourne, Brisbane, and Perth and Adelaide. So major city, we have at least one desalination plant. If you look at the numbers, desalination and water reuse. Water reuse is about reverse osmosis. So this is the desalination capex in 2021. So you can see the $6 billion for the capex last year, and OPEX is $11 billion. Also, contracted capacity last year was 6 million cubic meter per day, and desalination operating capacity 79 million cubic meter per day. Also, water reuse, so wastewater reuse almost 9.2 million cubic meter per day. Water reuse cumulative installed capacity is 169 million cubic meter per day. So desalination capex and OPEX almost double, $11 billion. So seawater desalination and the overall desalination is a big market of we can also tackle for the designing as well as the saving a lot of energy and chemical. So if you look at the desalination Australia, already I explained this slide at the beginning of our lecture 42991. So we discussed about what's the history of Sydney water management, and this is the Sydney desalination plant. So we have one desalination plant in Tasman Bay near airports. And you can see when we had a very serious dam capacity low level, less than 50%, due to the severe drought in 2008. So we installed one desalination plant, capacity 250 megaliter per day, cost $2.1 billion. First operation was on January 2010, and operation shut down June 2012. The reoperation 70% dam level reoperation. We used to operate little bit 2019 because at the time we had also little bit of drought because of the dam level was almost 70%. That's the trigger point. We started to operate the desalination plant. However, after several months later, October 2019, so we was get the full of water in the Waragamba Dam and other dams. That's the reason why currently Sydney desalination plant is shut down. So until we have another trigger point of the dam level, so we are just operating as a minimum level, and then we have like insurance just in case to respond to our increasing the population, manufacturing factory, so that we will need more water. In this case, our dam water and river water, even groundwater and the recycled water would not be sufficient, so that we can utilize the desalination plant as much as we can. So this is the what we have a Sydney desalination plant. So this is the 6 major desalination plant in different cities in Australia, and some of them is fully operatable, and most of them still in standby mode because of too much water. So Gold Coast, Sydney, and Victoria, Adelaide, they are almost standby mode. And on the other hand, the Perth seawater desalination plant, Southern seawater desalination plant, so the area is they are basically very much drought area, so that they have operate this desalination plant since 1998. So they never ever stop. So from the beginning of the desalination plant until now, so they keep operating this seawater desalination plant. And this is the Gold Coast desalination plant, 133 million liters per day. And you can see the reverse osmosis main technology, and the configuration, open intake, drum screen, dual media filtration, 5-micron cartridge filtration, 2-pass SWR system, and CO2 remineralization. So this is the basic treatment process from the Gold Coast seawater desalination. One of the assignments, so you need to select which one is the best process diagram. So what's the screening, pretreatment, filtration, and the reverse osmosis, and the post-treatment process. So based on the other desalination plant in Australia, so you can select some of the useful your desalination plant process diagram. So Victoria desalination plant, so we have diameter of the this screening, dual media pressure filtration, cartridge filtration, two-pass seawater reverse osmosis membrane, and then lime, and then CO2 remineralization post-treatment. And Adelaide seawater desalination plant, 300 megaliter per day, and they consist of the intake, outflow, also ultrafiltration. So compared to the just dual media filter, other plants, Adelaide consists of UF as a two-pass SWRO system. So ultrafiltration is utilized for treatment. Also, capacity is lime, CO2 remineralization. Also, this is the pulse seawater desalination plant. They have a open intake, diffuse outflow, and screens, dual media filtration, was cartridge filtration, RO, lime, and CO2 reverse remineralization. Was a southern seawater desalination plant near Perth. Also, they have a similar process, but this one has ultrafiltration as a pretreatment, and then reverse osmosis, lime, CO2 remineralization. So that's the 6 desalination plant we have in Australia. Is a major desalination plant, which is more than 100 megaliter per day capacity. So we will have a more desalination plant in the future. For example, like in Newcastle, Wollongong, so a little bit of a smaller city. Also, they will need a more stable and sustainable water resource. And then seawater desalination plant would be the one of the most sustainable water resource you can produce, just in case if you have a very severe drought, so that possibly we also consider this area could have a seawater desalination plant maybe next couple of decades. And this is the seawater desalination plant, and you can see the near airport. And this is the desalination capacity. You collect the water from Tasman Sea, and then you have a process, pre-treatment and reverse osmosis, post-treatment, and then you store water in this tank and then supply to our area. Already you have tasted your seawater desalinated water in this city. So it was 2009 to 2011. If you drank the tap water, it was already contained 15% of the desalinated water. So you can see the Sydney desalination plant located in Cornell, and then we collect water and we supply in the Sydney Park and distribute to desalinated water in this city. So let's look at how this Sydney desalination plant works. Let me share video. Can you see the video?
Yes, Professor.
Can you hear the sound?
No.
No. I'm trying to, yeah. Has to be. Has to be there. Can you hear sound?
No, Professor. Not yet.
Not yet. Okay. Okay. Let me show you. There is just some. I can share there is some text that you can see. So you can watch the video. So this is the seawater desalination plant, dams, recycling, desalination, water efficiency. So can you read all the text, right?
Yes.
That's good. So everybody was able to hear the sound, right?
Yeah.
Okay. Great. So very much familiar about the Sydney desalination plant, how they produce the seawater, and then how they process as a pretreatment and reverse osmosis, and goes to the next post-treatment that's applied to the Sydney Park, and then 50% mixed together with some dam water or fresh water, and then everybody get benefit from the desalination water. So let's go for detail. So how this Sydney desalination plant, Gold Coast desalination plant processed the seawater intake. First, we need to chlorinate, because the chlorination will kill all the bacteria. So you can reduce the biofilm in the pumps and then pipeline. Also iron chloride dose and pH adjustment and dual media filter, anti-scalant. You need to put some anti-scalant because we want to remove your salt almost 2 times, which means 50% water will be recovered, so that the salt concentration will be high. So if you don't have anti-scalant, so that you can create some kind of inorganic scaling and dechlorination and reverse osmosis module post-treatment with lime. Mostly lime is calcium hydroxide or calcium carbonate, and we need a buffer, otherwise your water is very corrosive in your pipeline. So it'll make sure that the buffer solution by this lime, and we chlorinate again, and then fluoride to remove the cavity, and then we supply your water. So if you look at the pH, so what's the pH of the seawater is around 8. So if you look at the chemistry, this is the bicarbonate and carbonate and CO2. So now there's a lot of climate change, increase the CO2 level. So what happens is the CO2 concentration is higher, and then you have a more low pH of your ocean, which can create the more problem of your coral and reef, because they cannot create some enough bicarbonate and carbonate to make their own living organism. So this pH in general in seawater, we have a pH 8, which is the mostly HCO3 bicarbonate contain the highest concentration. And this is the pretreatment. So you have a dual media filter or ultrafiltration. So dual media filter just similar to sand filtration or anthracite filtration or dual media filtration or triple media filtration. So this is the conventional and ultrafiltration. So you can see the capital cost and the O&M cost, energy cost, chemical cost. So you can see how much it requires for the conventional pretreatment, the ultrafiltration, membrane pretreatment. So ultrafiltration has already you studied membrane bioreactor, which is the very similar microfiltration or ultrafiltration. So you can select one of them as a pretreatment conventional dual media filtration or ultrafiltration, so that you can have best pretreatment as a quality. Already I explained to you, we have a 6 desalination plant in Australia. So we have 2 of them, like Adelaide desalination plant and Southern desalination plant. They have ultrafiltration as a pretreatment. And then most of them, 4 other desalination plants, consist of dual media filtration or anthracite filtration as a pretreatment. So they have their own merit and then cons. And then so far, yeah, this ultrafiltration is a little bit expensive, but they produced very consistent of your water quality, and your reverse osmosis membrane fouling is less than conventional. So your water quality in your seawater, if it's very high total dissolved solid or a lot of suspended solid, so it's better to go for ultrafiltration and then make a very consistent pretreatment. Otherwise, if your seawater quality is already good enough, and then you can go for your conventional treatment, and then you can protect your RO. So depending on your initial seawater desalination plant, and then your seawater feed water will be a good indicator how you can decide your conventional pretreatment or advanced pretreatment ultrafiltration. And this is your process. What happens is the anti-scalant. So this is if you don't have anti-scalant, as I mentioned, we remove the water, fresh water from seawater. Automatically, it increases the overall salt concentration. So calcium carbonate and then calcium sulfate and magnesium carbonate can be observed on your reverse osmosis membrane, so that they will be clogging your RO. So you need to look at how anti-scalant can be combined depending on your water chemistry. So sodium hexametaphosphate, so we just say SHMP, is a hexamer of the composition of the sodium phosphate. So what happens is that the sum of the calcium and magnesium, they are one of the problematic inorganic scaling. So calcium can be replaced with the sodium here, and then they can observe your calcium material, which will produce your inorganic scaling, like a calcium carbonate, calcium sulfate, or magnesium carbonate, so that you can have a better membrane filtration system. So depending on your seawater quality and the water recovery, and you can consider to incorporate the anti-scalant in your system. Also dechlorination. So we have a chlorination here. So we add a chlorination to reduce the biofilm in your pumping, in your pipeline, in your filtration system. And we have to remove chlorine, so which we call dechlorination. So what happens is that this chlorine is strong oxidation. So you kill your bacteria and you oxidize your organic. And what happens is that dechlorination will also remove your oxidation active component from chlorination, because this chlorine can damage your reverse osmosis membrane. The reverse osmosis membrane is basically polymer. So this polymer can be oxidized from your chlorination. So before we enter your water to reverse osmosis, you need to dechlorinate to remove your chlorine so that you can protect your reverse osmosis membrane. Otherwise, the membrane will be degradable, and then you will have a larger pores, and then you can reduce the overall salt rejection. So that's the how this reverse osmosis can be protected from the dechlorination. So this is the chemistry. You have a chlorine, and then dechlorination, we add SPS, sodium metabisulfite. So this chemical, we just dose 3:1 ratio of the SPS to Cl2, and reaction time is about 2 minutes. So you can see the how much they can reduce the Cl2 can be converted to the 2HCl, so which means chlorine is the very strong oxidant, and then very strong your oxidation property. But when you combine with the SBS, and then it converted to the just the normal HCl, so no more oxidation. So that's the reason why we reduce your chlorine oxidation property, and then dechlorinate it and goes to the reverse osmosis. So Cl2 change to the just the normal salt like the chloride. Also demineralization. So you have a post-treatment with lime. So why we have to utilize the demineralization, because the reverse osmosis remove the most of salt, like a calcium, magnesium, even sodium and chloride. So we need to mineralize. The water is very much not stable because no buffer solution. So in this case, what happens is the high corrosion potential you have. Also, you have a dietary deficiency causing risk of some heart disease. So you need to also have a more demineralized water. So WHO recommends 10 milligram per liter of magnesium and 30 milligram per liter of the calcium for drinking water. And you can protect your pipeline. So you can add CO2. CO2 creates the carbonate, so HCO3 or CO3 minus. So you can add the CO2. So depending on the pH, CO2 can convert to bicarbonate or carbonate. And then calcite limestone, CaCO3, and filtration or sodium carbonate. Or you can put also calcium chloride or sodium HCO3 can be combined for your post-treatment. That's why you can produce your safe remineralized water. And disinfection again, fluoride to remove the cavity in your teeth. And you have also chlorination to supply your water distribution system. So this is the annual operation and maintenance cost, mostly energy. Because of high osmotic pressure, energy is the most largest portion of your operation and maintenance cost. So you remember the number of the desalination. So last year, 2021, so we spent O&M cost $11 billion in the world desalination plant. So mostly 50%, let's say almost $6 billion we spent for energy. So that reducing the energy for your desalination because of the high salt, high osmotic pressure, and then you need a high pressure to produce the fresh water to separate the salt and water. That's the reason why. How we can save energy will be you can save $5-6 billion per year in your desalination plant. So let's look at the terminology when you design your desalination plant. So you can also look at some specific terms. for your membrane process. So we just use flux. Already you studied flux in your membrane bioreactor, liters per hour per square meter. So NMH and permeate water treated by membrane. And we have also concentrate. So concentrated waste from membrane. So you have a permeate, pure water, and you have a brine or reject or concentrate. So you have a very high salt concentration, which is almost double salt concentration. And recovery is also very important. So when you design recovery, you permeate to feed water, and TMP, transmembrane pressure, driving pressure across the membrane, and transmission is equal to passage of the certain solute across the membrane. Also unit, we just say the grouping of the membrane and buses with common feed pump piping control. So when you design 100,000 cubic meter per day, so what happens is that you don't design the 100,000 cubic meter per day, one design parameter. So we just split 100,000. So we just design 10,000 cubic meter per day or 1,000 cubic meter per day with the one unit, so which contain the pump, piping, control system. So we just group it. So you have a 10,000 multiplied by 30. So 30 unit, we will produce the 300,000 cubic meter per day. So unit is the, you don't design the whole capacity, just make a smaller unit, smaller size, and you can also have a better and then correct design. Also, you can have a redundancy, and you can have also contingency planning of the your unit operation. And we have element, individual membrane unit, and module, individual membrane unit, microfiltration, and ultrafiltration. So when you design the membrane bioreactor in your assignment 2, so you mentioned about module, but in reverse osmosis and nanofiltration, we just consider as an element. So module and element, sometimes people just utilize the same meaning because it doesn't really make a very big difference. This is a microfiltration, and this is RO, reverse osmosis. So module and element, one kind of membrane module unit. So we can say element. How many elements you need to design Sydney desalination plant? So you need to design 250,000 cubic meter per day. So how many elements do you need? That's the, we need to also design for your assignment 3. Also cassette, CIP already you are familiar, backwashing for microfiltration, enhanced backwashing. So that's the terminology we can utilize for our seawater desalination process. The water quality also very important. As I mentioned, water chemistry can decide how much water recovery we can set. Also, what's the problem of your water quality? What kind of pre-treatment we have to use? What kind of post-treatment we have to use? So that's the essential water quality parameters: turbidity, total organic carbon, silt density index, TSS, iron concentration, manganese concentration, silica, chlorine, and temperature, and oil and grease pH. Additionally, carbon dioxide and bicarbonate and carbonate was the buffering condition for your post-treatment. Also acidity and alkalinity, hardness, phosphorus, TDS, osmotic pressure, barium sulfate, strontium sulfate, disinfectants. So that's the overall additional parameters you have to consider carefully. So why this parameter is important? Because you have scaling, also fouling, and you have also water viscosity and density change. So let's think about hot water. So when you operate your desalination plant in Saudi Arabia, so Saudi Arabia, let's say we have a seawater temperature is almost 40 degrees. But if you operate your desalination plant in Melbourne, so you have a seawater temperature is around average 20 degree or 15 degree. So you have a temperature difference when you design your plant in Saudi Arabia and Melbourne. So you have a temperature difference in your seawater. So this temperature will affect overall your viscosity of your water. So seawater, when you have a temperature less than 12 degrees, the significant increase of the unit energy use because you increase your viscosity. And then when you have more than 35 degrees, so you operate the seawater desalination plant in Saudi Arabia, and this causes accelerated mineral scaling and biofouling because temperature is high, and then you have also more organic microorganism. So this will have a more dissolved mineral, so that you will have a more fouling and scaling. But when you have a less than 12 degree, you have a high viscosity, which means your water cannot pass through your RO membrane easily. So you have a high temperature, you have a high low viscosity, so which means you can pass through your water in your reverse osmosis membrane very easily. So when you have a 1 degree difference, so your flux, water flux in general, you can increase almost 10% of your overall water flux. So when you have a high temperature, your design parameter is different. Also, the problem is different. Scaling, biofouling, the energy cost will be high when you have a very low temperature. So this kind of water parameter will give you how you can make a better design. But as you already mentioned, you don't have enough water chemistry background. You don't have enough chemistry scaling issue or some viscosity, because you have to look at your books, or you have to look at the references, but it's very time consuming, so that you don't have to worry about your chemistry background. As long as you understand, okay, water quality will affect your overall design of the seawater desalination plant, and then each parameter will be carefully considered, and then you can put your concentration in your wave software, and then this wave software will tell you, okay, you have to be careful about this kind of scaling issue. Also, your energy cost is very high because of your temperature is low, and then your iron compound hardness and alkalinity, and then some of the osmotic pressure will tell you what could be the issue in your design. So if you know what's your overall concentration of the water parameters, and you will put into your wave software what's the concentration of turbidity, concentration of the total organic compound, what's the silt density index, so, and then what's the TSS, TDS. So in this case, you can automatically calculate in your wave software. so that you don't need to worry about a lot of your chemistry background, because your computer aided design will tell you what's the issue of your design. So if you know what's the concentration from the water analysis, and then you can easily utilize your software. But with better to understand how this temperature effect, pH effect, and then other compound effect for your design, so that you can have a better explanation. And then, so that's the wave water quality parameter. So you just collect your seawater from Bondi Beach, and then give to the analytical center, and they will measure what's the ammonia concentration, sodium concentration, calcium, and barium. Also, you have anions, carbonate, bicarbonate, and nitrate, and fluoride. So how this concentration can be entered in your software? What's the temperature, what's the turbidity, and the TDS, and then silt density index, and what's the pH, and the seawater and wastewater and water salt type, how this kind of feed water parameter you have. Also, you have a neutral like a boron and CO2 and then silica, and you will get the better of your design. So this feed water quality will automatically calculate your reverse osmosis recovery, and then your summary report will tell you how much fouling you have, how much problem you have in your water quality, so that we will have a better idea how we can respond to your overall RO membrane based on your water quality parameters. So that's the overall web software. That's the reason why we have to utilize and then familiarize, because that's the initial step before you try to look at the very much in-depth pilot scale demonstration or detail your larger scale. So this software without any experiment, so you can simulate, and you can save a lot of your time and your budget to look at the overall your design of the seawater desalination plants. And this the so far what we have look at how we design, what to know about your water quality, and then how the process diagram works. So do you have any questions so far? No, everybody is clear? Okay, so let's go next topic, which is seawater reverse osmosis. So as we discussed, the reverse osmosis is most powerful technology for seawater desalination as well as the wastewater reuse. So this history is of 1956, and then almost more than 70 years. So we developed the first RO membrane during this time, 1970. And then RO membrane has been used for last almost 60 years. And at the time, the energy was 10 kilowatt hour per cubic meters. And this energy cost was higher than the evaporation. So oil price was much cheaper, and then you just burn the oil and then boil your seawater, and you can distillate. So the boiling water using oil was much less energy cost compared to RO until we developed first energy reduction process to RO for energy recovery device. So this is the first innovation of the reverse osmosis. And then we reduced the overall energy like up to 4 kilowatt hour per cubic meter. So this is the timing. We reduced very significantly for energy cost using energy recovery device. So first generation from distillation to RO, even though it was still very much high energy, 10 kilowatt hour per cubic meter. So when you consider you pay around $0.35 for 1 kilowatt hour energy cost. So 10 kilowatt hour is almost $3.5 to produce the desalinated water 1 cubic meter. So that your reverse osmosis innovation was the first. And then second one is the energy recovery device. So nowadays, most of desalination plant, including the Australia, 6 major desalination plant, consist of reverse osmosis because it's very energy effective. So you can see the reverse osmosis can remove the ionics. So you can see what's the relative size. So this is the coronavirus. It's around 0.1 micrometer size of the virus. So if you want to remove the coronavirus, yeah, at least you need to utilize your membrane around 0.1 micrometer. But reverse osmosis, nanofiltration, you need to remove metals. You need to remove the sodium. You need to remove the chloride, monovalent ions, divalent ions, and trivalent ion, so that you need to have a very smaller size, like a 0.6 nanometer, 0.7 nanometer. So that's the reverse osmosis and nanofiltration. So nanofiltration is the little bit larger pore size than reverse osmosis, but basically they are same mechanism, like a non-porous membrane, and they have a symmetric structure, very thin film composite. So let me also show you some information how this reverse osmosis membrane works to separate your salt water to fresh water. So let me also show you one animation. You will have a very clear. So all the video is available on the canvas, so you can also watch from your video from the canvas. So what's the Let me share. Can you see the video?
Standard spiral.
Hello?
Oh yeah, we can.
Can you hear?
Wound membranes.
And we can hear it also.
Okay, you can hear. Okay, that's good. So we can start. What's the reverse osmosis? How this technology separate your water molecule with your salt. So this will give you a very clear idea.
To create our standard spiral wound membranes, we construct the flat sheet membrane using Hydronautics automated casting equipment. The membrane with additional elements to complete any number of design specifications. Once the end adapter is connected to the last element and the pressure vessel is sealed, feed water can be introduced and then treated. The feed water that does not permeate through the membrane becomes enriched in salts as it travels through the feed channel spacer due to permeate water being removed. Typically 8 to 10% of the water is removed in one 40-inch long membrane element. The permeate water then flows out the end of the vessel and is collected as the product. And the reject or concentrate from that vessel may then flow through another vessel producing more permeate. The remaining concentrate may then be disposed of as waste or partially recycled as the feed. Typically 70 to 90% of the water can be recovered as pure product water.
So this is exactly you need to design for your assignment 3. Already you look at the element. How many elements in one pressure vessel? So we have around 6 to 7. And then, so your water is passing through, and then you can recover 50%, 70%, 90% pure water. And you need to design what's the problem of your overall flow of the concentrate and the permeate. And then that's exactly your assignment 3. How many elements you need? How many train or unit you need? How many pressure vessels you need? That's we can also consider for your assignment, so that we can make sure that confidently design your 250,000 cubic meter per day of the Sydney desalination plant. So that's what we are trying to challenge. All right. So do you have any question on the video? So now is you quite well understood what's the RO membrane. So this is the polyamide. Just say polyamide is very much specific chemical name, but just common name as a general term is nylon. So nylon, so you have your water, you have your cross of the nylon material. So nylon material can create the artificial polymerization, interfacial polymerization, and then this polyamide can only pass through your water molecule and remove the salt. So this is the image of the microscope. So you can see the ultra thin dense skin layer. So that's exactly what we are talking about, polyamide membrane RO layer. And then bottom is the polysulfone, like a supporting polymer. And then backing layer is just the non-woven material. So skin layer is the most important active layer to remove your salt from seawater. So this membrane, we have a mass transport is diffusion, and we rely on osmosis. I'm sure there are a lot of people already know what's the osmosis, and concentration, polarization, and permeate flux. So we have osmosis. So seawater salt concentration is almost 3.5%. And this 3.5% is 35 gram per liter of concentration. And this 35 gram per liter of concentration, so osmotic pressure is almost 30 bar. So exactly 28 bar, but we just say roughly 28 bar your osmotic pressure you have. So which means you have to overcome your seawater osmosis pressure to produce your pure water permeability. So that's the reason why we need to look at how we can overcome this kind of osmosis. And that's the reason why you have to apply more than 28 bar, which means you have to apply 50 bar or 60 bar of your reverse osmosis pressure. That's the reason why you need a lot of energy to produce the desalinated water because of the osmosis. So let's look at what's the osmotic pressure. So this is the one of the example, cherry. So if you look at the cherry skin, so you can think about like a membrane skin. So water molecule can pass through your cherry, and then you can remain the salt. So what happens is that during your cherry timing, and you have a very high concentration of sugar. You just call sucrose or glucose. So glucose and sucrose also contain their own osmotic pressure. So when you have your cherry, your concentration is 1,000 milligram per liter. So you will have around 1.5 osmotic pressure. So you will keep expanding your cherry. So if you don't try to harvest your cherry, and then you have a rain, and then water is penetrate because of your osmotic pressure will suck your water in your cherry skin, and then you can damage your cherry. So you have more water and then keep expanding, and then finally it leads to your threshold of the mechanical strength of the skin of your cherry. That's the reason why we have to be careful. The right time you have to harvest, otherwise your fruits will be gone because of the osmotic pressure. So sodium chloride, osmotic pressure 1,000 milligram per liter, around 100 kilopascal, so which means 100 bar. So seawater 35,000 milligram per liter, and then 2,700 kilopascal, so 27 bar. That's what we have to calculate your osmotic pressure. So who developed the osmotic pressure? Van 't Hoff. So he developed this concept 1901, and this was first Nobel Prize in chemistry, which is the pi. Osmotic pressure is depending on your concentration of salt and ideal constant and temperature. So you have a 35,000 milligram per of the seawater, your concentration of salt, and then multiply by ideal. Already you know what's the temperature. So you know what's the osmotic pressure. You can calculate. So based on your concentration of your salt, even seawater, wastewater, even your blood liquid salt concentration, whatever liquid you have, so they have a salt concentration, so that you can easily calculate your osmotic pressure. And then this will also calculate how you can design your reverse osmosis. Luckily, in seawater desalination, we have a very consistent seawater quality all around the world. So around 3.5%, 35 gram per liter. So 35 gram per liter, even South Africa, Sydney, New Zealand, and Mexico, they have a similar concentration of seawater, so that we don't have to worry about this kind of osmotic pressure. Its osmotic pressure is around 27, 28 bar. However, when you consider wastewater use, so wastewater contain very diverse concentration of salt. So during the night time, during the morning time, during the lunch time, so every concentration varies. Also, they have a Monday, Sunday, and Wednesday. So you have a salt concentration, how people utilize the wastewater. So you depend on the what's the concentration. In this case, wastewater reuse, depending on the your concentration of your wastewater total dissolved solid concentration can be also calculated, and then you can decide the recovery ratio, the reverse osmosis membrane process design. So you have to look at carefully this osmotic pressure, and this is the osmotic pressure when you have your seawater concentration. So you have a permeate with the reverse osmosis membrane. So you have brine like a 50%. So in this case, the osmotic pressure seawater 36 milligram per liter 30 bar, and the energy consumption because of your osmotic pressure, and this is the 3.5 kilowatt hour per cubic meter required as a theoretical limit. The recovery is 0.5% of your brine. So you concentrate almost double. So 72,000 milligram per liter of your brine concentration you will have as a 50% of your recovery rate. So that's the osmotic pressure we can calculate from here, and how it changed along with the membrane, and then we can easily calculate our recovery ratio. Also, concentration polarization. So this is the important concept because we really cannot calculate this kind of detail, because when you have a membrane here, this is RO membrane, you have a seawater here, and this is salt. And what happens is that salt concentration is keep accumulate on your membrane surface. So which means your solute concentration at the membrane surface here is higher than bulk concentration. So when you have a distance from membrane to your channel, and you have a different concentration variation. So this is the concentration polarization layer. So you have a different osmotic pressure because they have a very high concentration polarization here, less concentration polarization. So how we can calculate this kind of concentration polarization? So we have a little bit of rough calculation. Bulk concentration normally we utilize as a manual, but when you have your wave software, so this software also consider how this concentration polarization will occur, and then you will have more detail overall your osmotic pressure on the surface of your membrane. So that's we need to understand bulk osmotic pressure and membrane surface osmotic pressure are different, and we can also design the different element. So standardization of element design, we just say normally element, one element BW is a brackish water 40-40. So 40 means this is 40 inch and 4 inch. So one is the 4-inch diameter, which is 5 centimeter diameter, and then 40 inch, 50 centimeter. So one element, brackish water element is 4 diameter, 4 inch, and the 40-inch length. So that's how you can select the different element. Also seawater 2.5 inch in diameter, 40 inch in length. So depending on your total capacity of your water, so you can select your element. Also, we have a 80, 40. So different element will have a different their application depending on your total capacity of your design. So we need to understand how this standardization can be utilized to select your element, also compatibility, pressure vessel, and handicap, simple design, the R&D benefit, all end user and manufacturers. Also, lack of diversity is very bad if you don't have enough diversity of your element. But let's look at also one more video, how this element can be manufactured and fabricated to have their own design. Because when you design your assignment 3, you need to answer the question, how many elements you need. So you need how much water, then you need to design your membrane surface area. So one element has this much of the membrane surface area, so that we can understand better way of how this element can be manufactured. Just a second. So far, everybody following well?
Yes.
Yes,
So
Professor.
it's everything is clear. If you have any question, yeah, just yeah, jump into my lecture, and then we can have any question, and we can discuss. Otherwise, I'm just talking to my screen and the monitor. So sometimes it's a little bit of a one-way lecture, so it's boring. So you can ask questions some of my lectures. Let me share that. How to make
Corporation, a
it's
subsidiary of
now
the
you
Dow
can
Chemical
hear, and then
Company,
you can
is the
also
world's leading
see the video,
manufacturer
right?
of reverse osmosis and nanofiltration membranes. Our products are used in a wide variety of industrial, municipal, residential, and commercial applications, helping Dow achieve its mission of improving what is most important in life, the human element. Our cutting-edge manufacturing technology improves the performance and quality of our membranes and provides the scale and infrastructure to serve the rapidly growing demand for RO and NF membranes. Providing high-quality membrane products starts with quality raw materials from ISO-certified suppliers. FT30 thin-film composite membrane, invented by Filmtech nearly 3 decades ago, is the genesis of today's industry standard. With each new generation of manufacturing equipment, the quality of film tech membranes is continuously improved through advanced process automation and control, from handling polyester-based material through casting the microporous polysulfone support to the complex polymerization reaction that creates the polyamide membrane layer. Design innovations allow us to use advanced membrane recipes that improve membrane performance and consistency. Dozens of critical variables are controlled and inline quality checks are performed to produce consistent, defect-free membrane without patching, and giving FilmTech membrane the widest pH cleaning range in the industry. A spiral wound membrane element can be fabricated manually or automatically. Dow uses custom-designed precision rolling equipment to automatically fabricate FilmTech elements because it allows for better, more consistent element performance. Sophisticated robotics for leaf construction and assembly ensure that every element is precisely built without membrane damage that often occurs during manual handling. Automation enables construction of more shorter leaves compared to manual rolling, resulting in a more efficient product that is less prone to fouling. Precise computer-controlled glue lines ensure the highest active area in the industry with guaranteed accuracy and minimize leaks, which can result in poor permeate quality. FilmTech elements are optimized to have the highest active area combined with the thickest feed spacer in the industry, offering several operating benefits, including improved cleanability, lower pressure drop, increased durability, and the ability to handle more challenging feed waters. A unique barcode allows continuous tracking of each element. Online quality checks for scroll integrity and dimensions and an inline vacuum test are performed on every element to ensure mechanical integrity. Any elements failing preset measurements are discarded. End caps are welded to the product water tube in a process that improves element strength, and a quality test ensures weld integrity. Our automated fiberglass process ensures exact and uniform fiberglass application within controlled dimensional tolerances. To validate final element performance, FilmTech uses both a traditional 20-minute performance test and a groundbreaking pulse integrity test, which has the unique ability to detect and diagnose mechanical defects. Tests are computer-controlled, and elements not meeting defined test ranges are discarded. Custom-designed packaging equipment combined with precision-injected preservative ensure protection for elements during storage and transportation, and easy handling. Prior to shipment, product for each customer order is scanned for traceability and to validate all previous quality checks. Quality is built into every FilmTech element, from the management of raw materials to final shipment. Every element undergoes multiple inline quality measurements, and additional parameters are measured based on defined sampling plans. Our technology enables a robust, consistent, defect-free membrane with the industry's widest pH cleaning range. Automated precision fabrication enables elements with maximum guaranteed active area, the industry's widest feed spacer, shorter membrane leaves, consistent high-integrity construction, and ILEC interlocking end caps. Collectively, these features enable consistent, reliable performance of RO systems with reduced system capital and operating costs. With the infrastructure to meet the rapidly growing demands of the market and the technology framework for integrating future innovations, Dow continues to lead the industry in reverse osmosis performance and value enhancement. Our goal is to offer the best membranes to enable the highest quality water at the lowest total cost. Innovation, automation, quality. FilmTech.
So this is the, can you hear me?
Yes, Professor.
Okay. So this is the most typical manufacturing process for reverse osmosis membrane. So you can, this is very typical 1 meter length and then 10 centimeter of diameter. And you can purchase, this is only $1,000. So you can utilize this module almost 5 years. That's the average lifetime of your membrane. And then every day you can produce almost 10 cubic meter per day of the desalinated water. So that's the how you can calculate your overall design of the element, and then we can easily make some kind of the design parameter to look at how many elements. So this information will be given by the manufacturing companies. So you don't have to worry about, because they already list out all the detailed membrane rejection, membrane surface area, and overall performance, water flux. So we can get the basic information, and then you can run your software of Wave. That's how it works. Okay, let me. So this is the also pressure vessel. We call this is the pressure vessel. So you have element inside, and this pressure vessel should tolerate around 100 bar or a little bit less, so that it has to be very strong material, fiberglass or stainless steel, also a spiral wound elements in a one pressure vessel. So in one pressure vessel, so you can install around 7 to 8 elements. Also, pressure vessels can be arranged into banks with the desired number of stages or passes. So that's how it works. And this is one of the examples. So you have a 7 element in one pressure vessel. So what happened is that why the design of your element and the flux by manually is difficult is that the flux distribution, pressure distribution will be different from your water quality. Let's say your seawater is enter this pressure vessel, and then you pass the one element, second element, fourth element, and then already your brine is your very high concentration of salt. So you have almost 30% of the recovery, and then you have a further increase of your recovery, and then you have a very high concentration of concentrate. So your brine concentration is high, and the osmotic pressure is high, and then your pressure different. So initially we pressurized your pressure vessel at the beginning 60 bar, and then you have a pressure loss because of the water is permeate to your fresh water side, so that you have a pressure loss. And then when you reach to this discharging point, you have almost 50 bar pressure of your very low pressure. So you have a different pressure distribution, different flux distribution. So that's the reason why you have to utilize the computer software. So if you look at detail, what's the salinity concentration? At the beginning, very low salinity in your permeate, 100 milligram per liter of the total dissolved solid. At the last one, because of the accumulated of your salt, your concentration is high, like almost 450 milligram per liter. Also, your flux. Initially, you have a very high flux. Let's say around 25% of flux. But at the last element, because of the high osmotic pressure, high fouling potential, so you have less than 5% of flux fraction. So 25% to 5%, how you can get the different design calculation. Also, you have a operating condition has to be a little bit different. Also, what we know, first element, very high flux, and the last element, too low flux. So how you can calculate for your design? Then what's the implication for your overall range? So this is the one of the example of the pressure profile as a practical system. So you can see that you have initially water is passing through. This is the applied pressure. This is the osmotic pressure. And this is the driving pressure, which means net pressure. The osmotic pressure increase. And the overall, if you don't increase your applied pressure, your driving pressure will decrease more and more. So you have to also calculate what's the best way to control your applied pressure, first stage, second stage, and third stage using the booster pump. And this is the example. Initially, your pressure vessel element, they have a very high colloidal organic fouling, and then you increase your overall salt concentration, silica, and then some of the inorganic salt fouling, very high concentration. So excessive differential pressure can cause structural damage because of this kind of telescoping effect. And you can have this kind of design based on this concept of our reverse osmosis. So we already have a 2:10, so we can have a little bit of break. And if you have not installed your software after break, you can try to install your web software. So how many minutes do you want to have a break? 10 minutes or 20 minutes?
20 minutes is good though.
Okay, so you can have a little bit of bite and then you can install the software. So we will come back 6:30. How fast is 6? And then we will start again how to design, and then also we can practice some of the software operation. Okay, see you in 20 minutes later.
Okay, Professor.
See you.
Okay, bye. So anybody stay in the computer room? Or everybody stay at your home or your office? Hello? Can you hear me?
Hello, Doc.
Yes. Yeah. Everybody back?
I don't know about the others, but I'm back.
Okay. Ammar is back. How about Jonathan? Are you back? Amit, Jiaming? All right. So you are Amit, Ammar, you are at the office or you are at home?
No, I'm home.
Okay, so nobody has a computer room. So just can I ask a very simple question?
Yeah, go ahead, please.
So seawater concentration is 3.5%, right?
Oh, excuse me, doctor. What is it again?
Seawater.
Yeah.
Seawater salt concentration is 3.5%, right?
Yes.
And just wondering, whether this seawater concentration has been 35 gram per liter from when?
From the soil.
From the seawater.
What was the last part?
Last part is okay. From when the seawater concentration is 35 gram per liter.
Like since when?
Like 1,000 years ago, we have 35 gram per liter of salt concentration, but now is 1,000 years ago, 2,000 years ago. Yep. Then how much concentration was salt in seawater? How about 10,000 years ago?
Like with time, I think the concentration like increases, but like I don't know since when.
Okay, so that's very interesting, right? Because if you look at some of the history book, so it's like seawater concentration was even the Bible tells around 35 gram per liter. So at the time was 2,000 years ago. It's the same as now we have the same concentration of the seawater.
Like it never changed.
That's exactly we can say that most probably, when the Earth was born, and we had a lot of volcanoes and a lot of heating, and then produced a lot of gas, and this covers sky, and we had a lot of raining for several years or several decades, long back ago. At that time, all the dissolved salt, easily dissolved in the earth, can be washed out to ocean. So which means that when the earth was born, already we have very much washed out all the salt into the ocean, and then seawater concentration has been very much similar, maybe million years ago and today, because it's very huge amount of water, right? So that's the people can guess.
I also have a question. Are like all seas and oceans have the same concentration of salt?
So that's the good question. So when you consider Middle East country, so there is the like a Black Sea, right? Dead Sea, right? You remember Dead Sea?
Yeah, I know.
So
That's
that Dead Sea is they are closed, and then they just evaporate depending on the weather condition and the severe drought. And then Dead Sea concentration of salt is almost more than 100 gram per liter, right?
yeah, but like the Dead Sea is like a special condition because like it's a closed area.
Right. Okay, let's see Red Sea. Do you know Red Sea, right?
I also know the Red Sea. Yeah.
Yes. How about Red Sea? What's the concentration of the Red Sea?
I'll assume
Okay.
it's 3.5 also, but let me check.
So Red Sea was very much higher concentration than any other seawater, because if you see that Gulf area, and they are half closed, half they open, but the evaporation rate is higher than their mixing rate of the ocean to others. So that if you go to the Middle East, like Saudi Arabia and Qatar, UAE, their seawater concentration is almost 45 gram per liter. So compared to the Sydney or any other seawater concentration of 35 gram per liter, they have a 45 gram per liter of seawater concentration. So it's higher than, yeah. So that's yeah. It depends on only Middle East area. Yeah, they have a more higher concentration. Otherwise, Africa, the South Africa, they are very much similar seawater concentration with Sydney. Okay, so everybody, hopefully back to the class. And then we can start again. Let me share the slide. Can you see the slide?
Yes, Professor.
Okay, so it's good to hear that everybody back here now. Okay, so we can go for the next session. So this time we will make a little bit example of design of a wastewater treatment plant. So we can think about what's the production volume, permeate quality, system flexibility, and then membrane utilization with the recovery, flow rate, and then feed water parameters and free chlorine. So this is the technology used in RO system. So we just use the spiral round. Already you watched the video, And then we need to decide the sum of their own terminology. So we just say average permeate flux. The average permeate flux is a function of the permeate flow rate and then membrane area. So we can say that the NMH. So you have how much water is flowing, liter. And then this is the membrane surface area, square meter, and per hours. So 1 hour, how much liter you can produce from your membrane. Also, salt passage is equal to permeate concentration Cp over Cf, feed water concentration times 100. So we just say salt passage, and salt rejection is Cr, retentate concentration over your feed water concentration times 100. 100 minus, or salt passage is equivalent to your salt rejection. So you have also recovery rate. Recovery rate is very important when you design your seawater desalination, even wastewater reuse plant. You have a flow rate. Recovery rate R is the QP. How much water is permeate, QP, over QF. How much feed water times 100. So let's say you have a 100 cubic meter per day of the feed water flow rate, and then you produce the 50 cubic meter per day. So 50 and you have a 100, so that you can see how much you can recover your water. So 50%, 100 and 50, and then you collect 50% of the recovery rate. And then membrane element. So this is the membrane element, pressure vessel, and this is a unit. So we need to design. Okay, this unit can produce the, let's say, 100 cubic meter per day. So you can install how many units. So that's the exactly we have to look at it. And then your flow dynamics in RO element. So flow dynamic for a single element. So let's say feed water 8 cubic meter per hour going to the RO membrane module pressure vessel. And then you have a one element, single element, have a 1 cubic meter per hour permeate, and then 7 cubic meter per hour of the retentate. So you have a recovery 12.5%. So let's connect another RO membrane element, so R1, R2. So R1 was 12.5%. So let's look at the R2. R2 is 0.125, and then 1 minus 0.125, which means 10.9% recovery rate you recover for your water second element. So which means you recover 23.4% of the overall recovery rate. Okay, let's connect another one, element 3. So 0.109 times 1 minus 0.109 is almost, let's say, 8%. So 8% you can recover from the next element. So R1, R2, R3. So you have a series of your recovery, and then when you combine each element, you combine together with your recovery rate, and you can calculate 50% of recovery rate. So based on your calculation, you can easily look at how much recovery rate you can achieve from the different element, so that you can easily design how much overall recovery rate can be achieved from the 6 or 7 or 8 elements. So this is the RO system train, single stage pass system, two-stage RO system, two-pass RO system. So we can say single stage, single pass system, which means your feed water is coming and then split to 3 pressure vessel, and then you have a combined permeate flux, and then combine return tank. So we just say first pass, 1 permeate, and first stage, this is the stage, 1 stage. So if you connect again for RO membrane here, we just say second pass. And then we just say second return tank, which means the second stage, first stage, and then you put another RO pressure vessel here. Then we can say second stage, 2 stages. This is the first pass, second pass. So 2-stage RO system, stage 1, stage 2. So you can have a first stage and second stage, also first pass, and also you can have this is first pass at this moment. Yeah. But if you pass through one more here, RO membrane, which is second pass. So we can also say 2 stages to second pass. So why this is important? Because when you have a high concentration of boron in your assignment, so you can think about your first pass, the boron concentration is too high, so you need to go through another second pass. So you need to design second pass RO membrane. So that's the reason why we need to look at the first pass, second pass. Also, when you have a stage 1, 2, 3, why we need a third stage? Because we want to increase the overall recovery rate. So if you use the first stage only, your recovery is relatively low. But when you go through another second stage and the water is mixing again, and then your concentration polarization is less at the end of the element, and then you can get another water permeability and go through another third stage, and you will have another water permeability. So which means 85% recovery can be achieved from your third stage. First stage, you can achieve maybe 80%, and then you can achieve 83%, and then you can achieve the 85% or 90%. So depending on how many stages you have for your retentate and concentrate, so you will have a higher water recovery. The higher water recovery means you have saved your overall operation cost, and then your effective water recovery. So this is the more energy efficient process you can develop. And two pass, as I mentioned, so you have a boron concentration. The first pass permeate can be go through another RO vessel, and then we can go for the next permeate. So which means we have a second pass. That's the way how we can get the second pass water. And this is the energy distribution. So you have a water intake, 0.2 kilowatt hour, pretreatment, center filtration, or dual media filtration, 0.4 kilowatt hour per cubic meter. The reverse osmosis, almost 72% of the energy consumption we spend, because this require very high pressure and delivery and then discharge to the outfall. So that's the reason why the seawater desalination, we need around 4 kilowatt hour per cubic meter. So 1 kilowatt hour almost $0.35 to utilize this 1 kilowatt hour. So which means you spend almost $1.2, $3 of energy cost you have to invest to produce the 1 cubic meter of seawater desalination. So that's a little bit expensive from the your desalinated water. So if you look at the energy calculation, so we have several methods to calculate energy. So one is the theoretical energy calculation, and the other one is the experimental pilot scale or larger scale operation of the energy calculation. So if you look at the seawater flow rate, applied pressure, RO recovery 40%, permeate flow rate. So you have a power required with our energy recovery device. I will explain energy recovery device. What is this one? Then you operate almost 300 kilowatt. The specific energy 300 over 40, and you have a 7.5 kilowatt hour per cubic meter. So without energy recovery, so you require 7.5. You have an energy recovery device, which is energy recovery turbine or pressure exchange energy recovery turbine. So when you have this energy recovery, you have a better energy saving. Almost total energy required 300 reduced to 177 to 140, which means when you use the pressure exchanger, you have almost 3.5 kilowatt hour per cubic meter, 50 to 60% of energy saving. So let's explain what's the pressure exchanger. So we can discuss about the pressure exchanger, which is the one of the innovation of the reverse osmosis technology. On the other hand, we can utilize the theoretical calculation of the energy. So let's say 70 bar of the pressure, then we have a flow rate 3 cubic meter per second. And then typical pressure for high salinity and the pump efficiency is around 80%. Then consumed feed pump energy is your flow rate and your pressure and pump efficiency. So 3 cubic meter per second, 70 bar, 7,000 kilopascal, and energy pump efficiency 0.8. So you need around 26,250 kilowatt hour per cubic meter per second. So you can just convert to your unit, and you can have a 7.3 kilowatt hour per cubic meter. So this is the theoretical calculation of your energy from your pressure, flow rate, and then pump efficiency. Okay, this value, we have a 75 bar, and you have a flow rate. So you can also calculate how much energy you require, 7.5 kilowatt hour per cubic meter. So that's the similar value we have. Excuse me. So you can have your pilot scale or a larger scale. Also, you can have a theoretical calculation of your energy. And already I mentioned about pressure exchanger. Theoretical energy value is this much, but seawater desalination is almost 3.5 or 4 kilowatt hour per cubic meter because of pressure exchanger. So how we can utilize this pressure exchanger, and then why this pressure exchanger save almost 50% of energy cost, energy consumption. So I will explain after this one. So we have 1 kilowatt hour, $0.29 in Australia, 4 kilowatt hour per cubic meter desalinated water. Energy cost of a Sydney desalination plant, we are designed to produce 250,000 cubic meter per day, which means $290,000 per day you need to spend for energy cost. So every year, how much you need to pay for your energy cost to produce your seawater desalination plant in your size of 250,000 cubic meter per day. So which means this is the really huge amount of energy it goes to the. So when you have a little bit of feeling of energy, kilowatt hours. So what's the kilowatt hour means? 100 watt normally this is the light bulb. Then 10-hour operation. So we just say 1,000 watt per hour, which means 1 kilowatt hour. So 1 kWh, and or you have almost 10 times 10 light bulbs and 100 watt, 1 hour operation, 1 kilowatt hour. So when you have 4 kilowatt hours, so how many light bulb you have? 40. So you can make a light for 1 hour with the 40 light bulb to consume the 4 kilowatt hour. So you can guess how much energy required for the seawater desalination. But this energy can be saved more than 50% because of this pressure exchanger. So let's just see how this pressure exchanger can be utilized. Can you hear the voice?
Yes.
Everything's okay, right? Okay, so let's start.
When seawater reverse osmosis, or SWRO, was first introduced, the membranes required very high pressure, pumps were inefficient, and control systems consisted of throttle valves that wasted energy. However, by far the greatest loss was the pressure energy leaving the process in the concentrate reject from the membranes. ERI's PX pressure exchanger recovers nearly all of the energy from the membrane reject stream and feeds it back to the SWRO process. Using just the energy in the reject concentrate, the PX pressurizes new seawater for the membranes, reducing the high-pressure pump flow requirements. This not only saves energy, it reduces the size and cost of the high-pressure pump. The reject concentrate from the SWRO membranes flows to the PX, where pressure energy is transferred directly to incoming seawater at up to 98% efficiency. Pressurized seawater from the PX, circulated with a small booster pump, joins the stream from the high-pressure pump. The energy consumed by the high-pressure pump, which is by far the largest operating expense of an SWRO plant, is reduced by about 60% by the PX. The PX is simple yet elegantly designed. The housing contains a ceramic rotor, the only moving part in the device. Surrounding the rotor are a sleeve and two end covers. These ceramic components fit snugly around the rotor, forming a tight seal that prevents pressure from escaping. Low-pressure seawater enters the PX and fills the rotor. This seawater is then exposed to high-pressure concentrate from the membranes. Pressure transfers directly from the concentrate to the seawater inside the rotor ducts. Spent concentrate leaves the rotor at low pressure, pushed out by fresh seawater. The rotor is turned by the flow itself, spinning at approximately 1,200 rotations per minute. The ducts of the rotor function like a carousel, charging and discharging as the pressure transfer process repeats itself. Water in the narrow gap around the rotor, which serves as a lubricant, is continuously replaced and refreshed. Mixing between the concentrate and seawater is minimal because the exposure time is so short. Overall, the PX Advanced Energy Recovery technology is the most efficient, easy-to-use, reliable solution to affordable desalination today.
Okay, this is how the pressure exchanger works. So you have this ceramic exchanger. So you have a fresh seawater. You have a very high pressure RO brine, and then they are meeting in the rotor. And then because of the pressure difference, they are very quickly rotating. And then you have a pressure almost room temperature, just atmospheric pressure, and you have a got to transport your pressure from the brine, and then you can discharge to your RO feed. So that's how it works for the pressure exchanger, so that you can save the energy almost 50% or 60%. So that's the reason why reverse osmosis is much more effective than boiling your distillation process of the desalination. And as I mentioned, we need to shut down and restart, because sometimes you don't need to operate your desalination plant, because of this is the very high energy consumption. So that if you have enough water in your dam, in your rivers, surface water, so we don't have to operate. So in this case, we can have a shutdown and restart planning. So with the dam storage level reaching to 90% capacity, the minister direct to the desalination plant to cease production for 1st July 2012. So more than 90%, yeah, we need to stop. But the dam storage level fell below 60%. It was happened 27 January 2019, and the Sydney desalination plant commenced the restart. So the Sydney desalination plant started delivering water to the Sydney water network March 2019 and reached to full capacity in August 2019. But the 8 months restart period ended 27 September 2019 because so we had enough rainfall, and then dam level was already good enough to supply the fresh water. In 2020, as rainfall stopped, the plant operation. So that's the exactly cycle. We cannot really predict when is the drought and when is the enough rainfall. So it's coming and going. So we need to well organize the shutdown and the restart. Also, this kind of dam level, you can go to the New South Wales water. So in the website, the real time, you can see the what's the Warragamba Dam capacity, dam level. How about the other dam? So we have around 9, 10 major dams near around the Sydney. So they are trying to communicate each other. And then based on that, we look at the dam level and how we can restart our Sydney desalination plant and how we can shut down depending on the dam storage levels. So that's the your another question in your assignment. How many times level of the your water and what kind of the restarting planning and shutdown planning? So it's already very well established. So you can look at some document, and also you can discuss about if you have any good suggestion or if you have any better solution, how we can effectively organize your shutdown and restart. So that's the summary of the Australian seawater reverse osmosis desalination plant. We have a 6 major desalination plant. What's the seawater concentration? What's the capacities? And then what are the RO configuration and BWRO system, RO recovery, SWRO, BWRO, and then what's the energy recovery device and total and the RO system, how this energy consumption we can achieve. So you can see those pressure exchanger of the most of energy recovery device, pressure exchanger or dual works energy recovery device. So we can also utilize different types of the energy recovery. So you can see the overall 3.4 to 4.2 kilowatt hour cubic meter of the seawater energy consumption we are currently operating. So that's the most of basic information of how we design the seawater desalination plant. So do you have any question so far?
No, Professor, no.
Okay, so if you don't have any question, so we can go for how to design our plant. So we can just practice one of the wastewater quality, and this can be also useful. You can try to do seawater desalination plant design. We have a plant capacity, cubic meter per day, feed water quality, TDS, and membrane properties. What's the average permeable flux, salt rejection rate, operating parameter, feed flow rate, recovery rate. So you need to have this kind of basic information to make a manual calculation. So when you go for your software, so at least you need to understand manually how this works, how we design. So just to give you manual simple calculation. Let's say wastewater reuse RO plant we want to design. Assume each train has a capacity of 300 cubic meter per day. Use wave to size the RO feed farm for one train. What conditions to use? And calculate the number of pressure buses, elements per pressure vessel, total number of elements. So that's the question. So we have to answer. So this is the membrane we have provided to your selection. Of course, you can select some other, but this is the most typical. BW 3400 membrane, feed water, secondary sewage effluent, TDS concentration 1800, water temperature is 25 degrees, and your production line cost volume is 300 cubic meter per day. So you need to design this train of your element. So we can have a reverse osmosis system analysis. So we have a wave exercise, step 1, 2, 3, 4, 5 to 10. So when you go for your RO design using your wave system, at least you need to have a very brief calculation by yourself. And then you can put the number in your software. Otherwise, it will be a very much difficult timing to put the random number. So at least you need to have a very basic understanding of how much your element roughly you need, and how much feed water quality you have. So overall information without any software, so you can have this level of basic manual understanding. So step 1 is that consider feed source, feed quality, feed product flow, and required product quality. So let's look at the membrane system design depends on the available feed water and application. So the system design information and the feed water analysis should be collected first. So you have what's the feed water source, SDI less than 3, surface water, SDI less than 5, and what's the SDI you have to find. Also choose the overall feed water concentration in TDS or individual ion. So you have a feed water concentration, what's the total dissolved solid or individual ion. So you can select. Also individual ion concentration from water analysis is always preferred because you can calculate your osmotic pressure better. Also, you can look at the membrane inorganic scaling potential or some of your membrane fouling potential. So individual ion or individual organic fouling would be very much important if you can. And we can select your flow configuration, number of passes. So the standard flow configuration for membrane system is flow because you pass through your element inside the pressure vessel. So we calculate as a flow type. A RO system is usually designed for continuous operation. The operating conditions of every membrane element in the plant are constant with time. And the permeate stage, the double pass system is the combination of the two conventional RO system, where permeate of the first pass becomes the feed for the second pass, which means we use the first permeate and then go through another RO, and then you have a second pass. So you can decide first pass or second pass. And you need to decide membrane and element type. The elements are selected according to feedwater salinity, feedwater fouling tendency, required rejection and energy requirement. The standard element size for system greater than 2.3 km per hour is 8 inch and 40 inch long. The smaller elements are available for smaller systems. So for the high quality water application, where very low product salinity is required, ion exchange resins are frequently used to polish our membrane. So if you look at the membrane type, TW, PW, SW. So PW means the brackish water, SW means seawater, and the SWHR is the seawater high rejection, and NF is nanofiltration. So this kind of membrane can be used. What's your TDS concentration? So seawater and very high seawater, high rejection. So you can see the almost 3.5%, 35 gram per liter of seawater concentration. And the brackish water is less than 5,000 milligram per liter. Nanofiltration is less than 1,000 milligram per liter, so that you can have a system of flow. So when you have a very high concentration, high your capacity, so you can use a larger diameter, 8-inch element. When you design the smaller capacity, so you can design with the small element, like a 5 centimeter diameter of the element. So you will get what's the permeate quality, and you can see also some of your overall permeate quality based on your membrane type selection. So you can select based on the seawater, brackish water. Okay, wastewater is BW. So that the previous slide, we selected BW30 400 membrane because of the wastewater use less than 5,000 milligram per liter, which will give your less than 50 milligram per liter of your permeate flow rate. And select average membrane flux. So our systems are usually designed for a specific permeate flow rate and a specific system recovery. So when you purchase the RO element, so manufacturer company, they already design for specific permeate flow rate, specific system recovery. So you can utilize that kind of information. And these numbers and the specific feed water source are the information required to estimate the number of elements and pressure buses and stages as flow. So select the design flux based on pilot data and customer experience or the typical design fluxes according to the feed source from membrane system design guideline. So you can have a design flux. If you see your software, I will explain later on. So already the database provide what's your design flux you have to use. So you can utilize the software database, so which kind of membrane average flux you can select and calculate your number of elements. The total number of elements needed is design permeate flow rate and design flux over active membrane surface area. So this will give a total number of elements. So you have a permeate flow rate 100 cubic meter per day, and design flux based on the manufacturer company provides your design flux, let's say 10 NMH, and then active layer of the surface selected element. Also, this is given by your manufacturing company. What's the surface area of the one element? In general, 50 square meter. So you can get the how many element you need to based on your design, what the flow rate and flux and membrane surface area. So this is the example for each element. Model number indicates the active membrane surface area, and Dow FinTech PW3400 element has a 37 square meter of the active membrane surface area. So this is given in your software so that you don't have to memorize this kind of the information. Also, you can easily ask the manufacturing company. They will give you what kind of membrane element is suitable for your application of the RO brine. Also, you can utilize the database of your software and calculate number of pressure buses needed. So total number of pressure buses needed is equal to total number of element over number of element in pressure bus. So round up to the near your integer. For the large system, 6 elements are standard. For pressure vessel with up to 8 elements are available. So for smaller or compact system, shorter pressure vessel may be selected. Also, although the approach described in the following section apply for all the system, it is especially applicable for 8-inch system with a larger number of elements and pressure vessel, which then can be arranged in a certain way. So small systems with only one or few elements are mostly designed with the element in series, and the concentrate recirculation for maintaining the appropriate flow rate through the feed to brine channels. So that's the select the number of stages. You can see the table. What's the recovery rate? 40 to 60, 85, 90. So this is the brackish water, which is the less than 5,000 milligram per liter of our TDS, which is the wastewater we use. And number of the element, when you have a very high system recovery, you have a very high serial element position, 6, 12, 18. The number of stage 1, 2, 3, you can achieve the very high water recovery. And then number of stage in seawater, stage 30%, 40%, 50%, more than 50%. So you can have how many number of the serial element also staging. So when you increase your seawater desalination for your design overall recovery, let's say you design for 50%, so you need the 2 stages. So when you have a less than 40%, you can have only 1 stage with the 6 element puzzle. But when you have a more than 50%, so you can design for 2 stages and the number of stages, 7 elements and 2. Also, you have a 8 element if you want to use, so you need only just 1 stage. So depending on the how many elements, 6, 7, 8, how many stages you can decide with system recovery. So select the staging ratio. So this is the ratio you can select. So when you have your stage 1, 2, 3, so how many pressure vessels you can make a staging ratio? So we just call array ratio. So for a system with 4 vessels in the first stage and 2 vessels in the second stage, the staging ratio is 2 to 1. So you have a 4 vessels and then first, and then 2 vessels in the second stage. So 4 to 2, which means 2 to 1 ratio you can use as a second stage. Also, when you have a 3-stage system with 4, 3, and 2 buses in the first, second, and third stage respectively has a staging ratio of the 4:3:2. In brackish water, staging ratio between 2 subsequent stages are usually close to 2:1 for 6 elements, less than that for shorter buses. In 2 stages seawater desalination system with a 6 element vessel, so typical staging ratio is 3:2. So you can have how many pressure vessel you need, and then you can calculate staging 3:2 ratio or 2:1 ratio depending on your element, and then depending on your water quality. So you can select your staging ratio. Also balance. So you need to carefully balance the permeate, concentrate flow, also your overall feed water. So how you can make a balance? Otherwise, you will damage your overall membrane. So it's like completely flow configuration, and you have a saturated system, and then you can easily balance your permeate flow, how much water is in, how much water is permeate, and how much retentate or brine goes to the next step. So you can easily calculate based on your software and the overall your flow rate. So that's how you can calculate from this kind of the balance, the permeate flow. And this is the example. Okay, we have discussed the 9 steps, how we can go for the designing of your membrane RO module and then element. So we can try with the example, so which will be very well aligned with your seawater desalination plant design as well. So given condition, feed source, so brackish surface water, STI less than 5, required permeate flow 720 cubic meter per day, 6 element pressure vessel to be used. We want to have 75% water recovery. So design your membrane plant, and you can also utilize the Wave software. So first step, okay, let's go one by one. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can follow one by one. So that's what I have arranged your information based on the steps. The breakage water, STI less than 5, total permeate flow 720 cubic meter per day. And then second step is the plug flow. Select. Then we have a BW30 element. So this is the database, the information 33 square meter, and the recommended average flux for this membrane element is 25 nmH with the condition of STI less than 5. So total number of elements 720 cubic meter per day, 40 liter per hours, and this is the 33.9 square meter, and this is also 25 the nmH of the average water flow. So you have a total number of elements is we need a 35 element. So we have a 6 element pressure vessel in one pressure vessel, and total number of pressure vessels is 35 element to 6. So we have a 5.83 pressure vessels. And then we can have a round up. So 6 pressure vessel we need. So number of stages for 6 element buses and 75% recovery. So we have more than 75% recovery stage 2. So we need 2 stages for 6 pressure vessel. So we will have a staging ratio 2-to-1 ratio. So which means 6 pressure vessel 4-to-2 staging ratio we need for this kind of information. So this is the 4-to-2, and we have a design for this stage ratio. The chosen system must then be analyzed using the wave computer program. So this program calculates the feed pressure and permeate quality of the system, as well as the operating data of all individual elements. So it is then easy to optimize the system design by changing the number and then type of element and their arrangement. So that's the basic information we can easily calculate, and then we can go for more detail. So how we apply this design parameter in a wave software. So this is the wave software. After you install your program, and then you will see this kind of first screen, and you can see what's the feed water, product water, what's the technology you want to select. At this moment, yeah, let's go for only RO. And then this is the seawater we want to use, and the feed water, how much you have, then what's the product water you need to do it. And then you just click the feed water, it's a home. It was previous slide was home. You click the second tab, your feed water. Already I discussed with you different concentration individual, what's the seawater type, and what's the conventional pretreatment and turbidity and TSS and the organic content. So this is the temperature and pH, and you can see the cations, anions, and neutrals. So you can get the overall feed water quality of the information. And this is already, we discussed about the overall water quality. I just want to emphasize the salt density index. So SDI is a calculated number based on filtration of a sample through a 0.45 micron filter pad, and SDI readings are used to indicate the fouling tendency of a water for use as a RO feed water. So SDI is calculated by following formula. The SDI 15 is we can calculate based on this equation. So T1, T2. T1 is the time in seconds to filter initial 500 millimeter of sample. And T2 is time in seconds to filter final 500 millimeter of sample. So you have a 0.45 microfiltration. So you have your feed water, and then first you can pass through the 500 millimeter, and then you can wait for 15 minutes. After that, T2 is you collect another 500 millimeter. So the gap of your water filtration will tell you SDI 15. So this is if you have a very high contaminated water quality, and then your SDI is very high. But if you have a very clean water quality, you have a very low SDI, which means less than 5. So when you have a less than 5 SDI, so you can utilize your pretreatment to go through your RO membrane. So most of the membrane design, so when you have a RO feed water, so you can try to reduce the STI less than 5, and then you can get your better performance of your overall STI value. That's how the people look at the overall water quality of the STI. And next tab, so you click the next step, reverse osmosis. So this next step, you can see different types of the stages, 1, 3, 5 stages. And you have also different level of the feed flow rate, recovery ratio, permeate flow, flux, and recycle flow and permeate split flow. So based on this kind of information, also you can give how you can select stage 1, what kind of the pressure vessel stage, how many elements per pressure vessel, you have 7. Then what kind of membrane element, you can click here and then you can select based on the seawater desalination or brackish water desalination or wastewater. And then you can have also flow rate and the recovery and the permeate and flux, so that you can get the overall diagram of your RO membrane water flow. And then you can have some of the calculation, and just you click the summary. After you roughly calculate all the overall value, and you can go for the summary report. If you click the summary report, okay, you will get this kind of information, our summary report. So you will see all the detail, how you design for your feed water, how you put the pretreatment, how you design the water flux, and then you can see all the water quality as well. So 1, 2, 3, 4, 5, 6, all the points, you can get your water quality data, water flux data, and the important information from your system design. So that's you can try. And if we go summary, then I can explain this one. What membrane do you select? Already we briefly discussed about reverse osmosis, PWRO, SWRO, nanofiltration. So you can have a rejection property of the RO membrane are fixed at time of the manufacture and only change as a result of age and damage. The manufacturers often different grades of RO membrane with the varying degrees of rejection, and product water quality from RO will change as a function of the following: like variable feed quality, variable operating flux, and variable process recovery. And list of the salt rejecting FIMTEC membrane from Dow Chemical, so nanofiltration membrane, brackish water, seawater RO. The general objective of RO treatment is to reduce TDS, remove the organic or softening. Also target TDS for water product is range of the 350 milligram per liter. And you have a membrane selection based on your TDS. Already we discussed about this one a little bit for based on the step 1, 2, 3, and then quantity consideration. When you have your system capacity more than 200 liters per hour, more than 2.3 cubic meter per hour, so you can select larger diameter of the element, 8 inch, smaller one is the smaller your diameter of the element you can select. And each membrane also you can have a operate within certain limit to minimize concentration, polarization, permeable flow rate below upper limit, and element recovery below upper limit, and concentrate flow rate above lower limit. So you can make sure this condition to minimize the concentration polarization. Also, to avoid the physical damage, so feed flow rate below upper limit, pressure drop below upper limit, and feed pressure below upper limit. So using our software, check the following. The feed flow rate per vessel in first stage is almost 12 km per hour. The concentrate flow rate per vessel in last stage is more than 3.6 km per hour. The individual element recovery between 8 to 14%. So we can design, so each element will contribute 8 to 14 recovery, and we combine all the total water recovery 50% or 40%. So that's how we can design. And this is the also second stage. Previously, we put the first stage, but when you increase your overall water recovery, so you can select first stage, second stage, or third stage. So mostly the wastewater reuse, if you want to use the high recovery more than 80%, 85%, or 90%, so you need a third stage. And if you want to have a seawater desalination, almost 40 to 50% water recovery, so you need a second stage. So that's the how you can have a more high recovery using the number of stages. So this is the first stage. And then your permeate goes to this next level. This is the concentrate, and this is the second pass. This is the second pass when you remove the some your boron concentration or some other high concentration of salt, and you can design the first stage and second stage different membrane, and then how this can be utilized your own separate the design. So if you click the stage one, so you can see what's the stage one recovery, then what's the bypass, and the second stage you click this one, then you can also calculate your flow rate recovery and different parameters. Also, pH is important because the seawater pH is overall 8, and then this 8 is easily you can make a hydrolyzed component so that the inorganic scaling is high. So we can reduce the pH to minimize your inorganic scaling. So in this case, so you can click your chemical addition. So you can put the pH and hydrogen sulfate, and you can have a pH 6, and you will have a lower RSI value. Overall, you have a not much inorganic potential in your water. But if you see this RSI 3.31, so this is the before adjustment. The after pH adjustment also we didn't adjust to 7.9. So low pH, it's around fresh seawater pH 8. The RO first pass concentrate after that. So we have around 9 pH. So in this case, RSI value has a red color, which means you will see the sum of the inorganic potential. So this is the LSI scale potential, negative less than 0, no scale potential, water will dissolve the calcium carbonate, positive greater than 0, scale can form. So you have a calcium phosphate precipitation may occur, close to 0, borderline scale potential, water quality and temperature changes, or evaporation could change the index. Input, the alkalinity, calcium hardness, total dissolved solid, actual pH. So you can see LSA value. What we are saying that from our previous slide, LSA value without any pH change. So we have a 3.31. So this is the positive greater than 0, which means scale can form, calcium carbonate can be precipitate. So LSI value can be calculated with the pH minus pHs. So pH 9.3 plus A plus B minus CDs. A is your TDS concentration, B is the overall your temperature, and C is your calcium carbonate, calcium concentration, and D is your alkalinity as a calcium carbonate. So based on this equation, so you can calculate LSI. So if it is more than 0, so you have a very high potential of scaling. Less than 0, you have a very low scaling. So you can see the different inorganic scaling on the surface of your RO membrane. So that's how you calculate the carbonate scaling. So that's after all the necessary chemical addition, inorganic potential adjustment, pH adjustment, and you can click the summary report. So this summary report will give you overall diagram, and then each point, what's the flow, TDS concentration, pressure, and then flow rate. Also, you can see the very detailed overview of your pressure vessel, pass 1, pass 2, how many elements you design, how many feed water TDS concentration you have, and then feed pressure you input, and then flow factors. So flow factor is normally we put 0.9. So what's the flow factor is that so you have a new membrane. So new membrane has almost 100% efficiency, but after 1 year and 2 years, so second hand RO membrane element, so you have a less performance. Let's say 90% of overall RO element performance. So flow factor in this case you provide 0.9. So this is like a pump efficiency. You have a pump efficiency 80%, 90%, and that every pump, so with time, so your pump efficiency will decrease. So flow factor is the same. So new membrane element, you have a 100% efficiency of the element, but with time, so you reduce the 80%, 90%. So that's how it works. So permeate flow per pass, and then average flux, and permeate TDS, and what's the recovery average net pressure, and the specific energy, how you spend your specific energy at the pass 1, 6 kilowatt hour per cubic meter. But after pass 1, your TDS concentration is very low, so almost 288 milligram per liter compared to your pass 1. So you will have very much low energy consumption, 0.57. So temperature and pH and chemical dose. RO system recovery, RO system also specific overall. We produced almost spend 6.98 kilowatt approximate method to produce this level of the water quality. So you can see the boron and then the silica concentration it does not include ammonia and CO2. Design include the permeate split, and then please refer to the RO system diagram. And this is also each stage like a F, R, and then what's the pressure vessel number, element number. So what's the permeate quality, and then what's the flow rate. So you can also see from your summary report. Also, you can see all the detail, like each individual ions. Ammonia, low concentration was 0.06. Just after pH, your concentration 0.06. And then concentrate, you have 0.06. The permeate is 0. The ammonia concentrate at the permeate, and you have a 0 concentration. And potassium, sodium. Let's see the sodium initial concentration 14 milligram per liter. After your permeate 37 milligram per liter. So you have a sodium concentration, each individual and different pH. How this pH change? So you can easily also calculate from your summary report. So each individual. So what's the problem in your assessment? We ask you whether you can satisfy 0.3 milligram per liter of boron concentration. The boron 5.16 initially, but after your stage 1F area, this is 1R area, and then after second pass, so your boron concentration is almost 0.5 milligram per liter. So still very high. So in this case, you have to also consider how you can reduce the overall boron concentration. So specifically, you have a targeted individual. So how they can be removed from your design of the RO plan. So you can also consider carefully. And this is the RO design earnings, the RO flow rate table, and this is the pass 1, pass 2. Then you can see how much they recover each element, then how much they also utilize the pass 2. So you can have a different information from RO design owning. Also, you can see the RO design owning is none here. So you have to also get this kind of the information. And this is the RO flow table. And this is the RO solubility earnings, RO chemical adjustment. And as we discussed, the LSI value based on our design. So pass 1 feed, RO pass concentration, RO second pass concentration. So you can see how they can be, consider what's the impact of the overall your concentration of the inorganic scaling potential. So based on the red color, then you can see, okay, we need to put the inorganic scaling or anti-scaling. So you can see the RO solubility owning. So your index more than 0, pass 1. LSI value more than 0, which means pass 2. So you have a very high potential of the calcium carbonate inorganic scaling. Magnesium hydroxide more than 100. So you will get the magnesium hydroxide percent saturation. So that also we have to consider anti-scalant may be required. So you can also discuss about this kind of inorganic scaling, what kind of anti-scalant we can add. and then we can measure the sum of the fouling potential in terms of your RO solubility. So that's the overall our lectures for the how to design a seawater desalination plant, so that now it's you already covered most of necessary information, how we make a first diagram, feed water, pre-treatment, RO, and post-treatment. So what are the important water quality indicator or water chemistry? And what's the water recovery? What kind of element you need? What's the concentration, polarization? What's the osmosis? And based on that, we can try to look at how you can make a better design of your seawater desalination. And then based on this basic information, we can go for the web software. And this web software will give you how you can make a more detailed information of your design. And then what's the flux, what's the rejection, what's the fouling potential, what's the inorganic potential. So all the information will be available from your summary report. So if you have a better design, and then you will see detail of the overall your capex, opex, as well as the overall your plant cost. So that's the very much useful initial step you can utilize from this software. Okay. Do you have any questions so far? You have no questions?
No, I don't.
You
Thank
don't
you.
have? Okay, so I want to show you the software. If you have any more questions, I will share the one more software operation, and then I can close these lectures. Is it okay? Can you see the screen?
Yes, Professor.
That's great. So this is the first screen. So you can, I will provide some example file. Also, you have a example file in the database in this software. Also, you can select some of based on the existing file. And I will select, let's say, seawater desalination example. So if you click the one of the file, and then you have a different seawater, wastewater, and you can select. So this is the reverse osmosis. So what's your feed water flow rate? Then how much you can produce, 50%, so you can select. With the pre-treatment, you can have a ultrafiltration, or you don't have a dual media filtration pre-treatment in this software, because that's the little bit different way of design. So that in this program Wave, they provide ultrafiltration as a pre-treatment. So this is the advanced one. So you can also utilize the same one, or also you have a specific application ion exchange pre-treatment, because you have a very high concentration of calcium, silica, magnesium based on your groundwater. So groundwater contain very high concentration of the calcium and magnesium, which will create a very big inorganic scaling issue in RO. So sometimes you may need to use ion exchange resin, but here I think that this is not necessary. So ultrafiltration, reverse osmosis, and you can also consider some of the CCRO. This is the new concept, closed circuit reverse osmosis. Also, this is the small commercial reverse osmosis, and this is the ion exchange, the demineralization. So you have a different demineralization, but in this class, we want to design reverse osmosis. So please select reverse osmosis. And then polishing, maybe if you want to have a more clear the salt removal, so you can use the ion exchange, the mixed bed, ion exchange condensate polishing can be used. Also split and mixed point, and then WQA, this kind of technology, you can select that you can put, but in your assignment, yeah, it's up to you whether you select your dual media filter or send the filtration system as a pre-treatment. So in this case, you don't need ultrafiltration. So you can just design your send filtration separately in your report. Otherwise, you can add your ultrafiltration in this system. But of course, you don't have to combine together. You can just use RO as a design of your process. But if you want to have a more combined design, you can incorporate. So what happens is that ultrafiltration tab increased in this tabs. And then when you remove this one, when you have RO, so you have only feed water, reverse osmosis, and then summary report. So you can select based on your preference. You can separate UF design, or you can incorporate UF design. So it's up to you for your assignment 3. And then you can have a feed water. So this feed water information is available in your scenario. So we have a scenario report. So you can utilize the scenario report, the basic water quality in seawater, and then you can have a good information. Also, this seawater, the water soft type, and you can have a turbidity, TSS, and the organic content has to be incorporated, and then temperature. Also, you can utilize your scenario report, basic information of your water quality, and ultrafiltration. So I didn't really teach this one because of the time limitation, but if you want to incorporate, that's fine. You can incorporate based on this software, but you already have experience with the membrane bioreactor. So what's the flux you can calculate, so which is very much a similar concept you can utilize for ultrafiltration. So you can incorporate, or you don't have to incorporate if you feel this is not your preferred pretreatment. And then reverse osmosis, pass 1, pass 2. So you can also have a different stage in your system, also feed flow rate, how you calculate your first pass, second pass, feed flow rate, permeate flow rate, flux, and then concentrate recite. And then based on that, you just keep trying to look at your diagram, first pass, second pass, stage 1, stage 2. So when you change the stage 1, so you can see the disappear. When you have a first pass, also you have only one module. So you can add the second pass because of the boron removal. And then you want to increase the stage because of your increase the recovery. So let's say first pass, you need to go for second pass. I think we don't need the second pass for your stage 2. Yeah, so that's the way, how you can play with your design. First pass, second pass, first stage, second stage, and then put your rough value of the feed flow rate based on your rough calculation, how much you want to design, and then you can put the summary, the pre-specified element. So if you have a problem in your design, so this will keep giving you error message. So that we need to make sure your design is correct. And then if you click the summary report, and you will get your design information. So, okay, this is the overall your design flow diagram, how much you have a different system configuration, RO system overview, what's the RO table, and then solute concentration, how much they decreased, and then what's the concentration change, and then what's the RO design warnings, and then special comment. So you can see all the detailed information from your summary. And then this is the RO solubility warning none. And then chemical adjust LSI value is almost 0 because we didn't really include in our permit. We just put the sodium and chloride. I didn't include any calcium, magnesium, or potassium, or bromide, sulfate. That's the reason why mostly RO solubility warning is nothing. And the RO chemical adjustment, we don't need because this is only sodium chloride. But if you put the detailed information of your calcium, magnesium, and then you will have some warning message, and you will have an inorganic potential. So that's how this summary will give you your overall assignment final outcome. Sorry. So that's you can utilize this wave software. So do you have any question for this software?
No, it's clear for me now.
It's clear, right? That's great. So now it's you need to go and then you need to install and practice your design, and then you will have a good kind of experience how to design your own way of the seawater desalination plant based on our scenario, and you can make a little bit more energy efficient, more innovative design using this software. So you will get a lot of information from this free software, and then have a very good knowledge of how the simple membrane RO can be designed from this wave software. So that's all about our plug 3. So after this class, I'm sure that you're confident to design a wastewater desalination plant or a wastewater RO desalination plant, because basically they are similar, just a matter of different feed water concentration. So we are using RO membrane. So you can think about how you can design using your step 1, 2, 3, 4, 10, and then going to your wave program, and then make a very professional report for your assignment 3. All right, so that's all about from today. And we have a consultation time. When is it? The 20th of June. So we can discuss about what's the problem and any other issues for your design of the seawater, and you can join the next consultation. Also, anytime if you want to have a personal discussion or individual meeting, just let me know. Also, I'm happy to have a face-to-face meeting, depending on your request, so we can have a better discussion. All right. Do you have any last burning questions?
Oh, no, thank you, doctor.
All right, so it's a Friday, and then you can have a good weekend. Also, we have a good Mother's Day on Sunday, and I hope that you can manage your block 3 and then assignment 3 on time, and then I will keep in touch with you to make a more better report and the better knowledge and skill for you. Thank you very much, and then see you next meeting.
Thank you, Professor.
Thank
Thank you,
you.
Professor.
Have a
Thank
nice
you.
week.
Have a
Take care.
nice one.
Bye.